Greetings and welcome to lecture 17 on the course Introduction to Fourier Analysis. On the previous lecture we observed that the Fourier transform of the constant function 1 is the Dirac measure. This showed that in order to understand the Fourier transforms of some simple and natural functions, we need to look beyond locally integrable functions. But where should we look at? We would like to find a class of objects more general than functions, so that their Fourier transforms are always objects of the same kind. And this class of objects is the class of tempered distributions. In preparation for the definition, we gave the space of Schwarz functions a topology and in fact a metric D. Then, at the end of the lecture, we showed that the space of Schwarz functions equipped with this metric is a complete metric space. Now we can define the space of tempered distributions. This is definition 4.7. A tempered distribution is any continuous, complex-valued linear map on the space of Schwarz functions, where continuity is defined relative to the metric D. The space of tempered distributions is typically denoted by calligraphic S'. For those of you who have studied some functional analysis, the space of tempered distributions is the dual of the space of Schwarz functions, equipped with the D distance. Let's digest this definition a little. The first remark is completely trivial. It is just a definition of continuity in a metric space. A complex-valued linear map lambda on the space of Schwarz functions is a tempered distribution if and only if the following holds. For all sequences of Schwarz functions phi j converging to another Schwarz function phi, the complex numbers lambda of phi j converge to the complex number lambda of phi. The second remark is that, since lambda is assumed to be linear, its continuity is equivalent to continuity at the origin. In other words, if you need to check the continuity of a linear map lambda on the space of Schwarz functions, it suffices to take a sequence of Schwarz functions phi j converging to 0 and verify that the values lambda of phi j also converge to 0. The next characterization of tempered distributions, theorem 4.8, is a little less immediate. Before going to the statement, we recall that a sequence of Schwarz functions phi j tends to 0 in the metric D if and only if the n norms of the functions phi j tend to 0 as j tends to infinity, for each natural number n separately. It's also worth pointing out that the n norms increase as n increases, because the n norm involves the summation over all multi-indices of order at most n. So the n norm of phi is bounded from above by the n plus 1 norm of phi, and so on. Now we can state and prove theorem 4.8. A complex-valued linear map lambda on the space of Schwarz functions is a tempered distribution if and only if there exists a positive constant c and a natural number n such that the following holds. The absolute value of lambda at phi is bounded from above by c times the n norm of phi for all Schwarz functions phi. The statement is actually quite remarkable. The values of any tempered distribution are controlled by one single n norm with a finite n. If you look at the definition of the n norm here, this means that if the derivatives of phi up to some finite order are very small, then also lambda of phi is very small. We then prove theorem 4.8. One direction is very easy. Namely, assume first that lambda is a linear map on the space of Schwarz functions satisfying the inequality in theorem 4.8 for some constants c and n. We claim that lambda is then a continuous map on the space of Schwarz functions. If phi j is a sequence of Schwarz functions which tend to 0 in the D metric, then in particular the n norms of the functions phi j tend to 0 for the natural number n appearing in the inequality. It follows that the absolute values of lambda at phi j, which are bounded by c times the n norms of the functions phi j by assumption, also tend to 0. Hence lambda is a continuous linear map on the space S, D. Let us then prove the converse. Assume that lambda is a tempered distribution. We claim that the inequality star holds for some constants c and n. To see this, we make a counter-assumption. There are no such constants c and n. This means that for every natural number n, we may find the Schwarz function phi of n violating the inequality with constants n squared and n. Namely, the absolute value of lambda at phi n exceeds n squared times the n norm of phi n. To show that this violates our assumption that lambda is a tempered distribution, we normalize the sequence phi n as follows. We consider the new Schwarz functions psi of n defined by dividing phi of n by the constant n times the n norm of phi n. Because the n norms are norms, we see that the n norm of psi n equals the n norm of phi n divided by n times the n norm of phi n, which is simply 1 over n. In fact, we can say a little more. If m is an integer between 0 and n, then the m norm of psi n is bounded by the n norm of psi n, which was equal to n. The first inequality follows from the fact, which we briefly mentioned before the proof started, that the n norms are in increasing order relative to n. From this inequality, we may deduce that if m is any fixed natural number, then the sequence psi n tends to 0 in the m norm. Namely, if m is a natural number and epsilon is a positive number, pick n to be larger than the maximum of m and 1 over epsilon. Then the m norm of psi n is bounded by 1 over n, as we just saw above, and this is further bounded by epsilon by the choice of n. We have now seen that the sequence psi n converges to 0 relative to every m norm, and this means that the sequence psi n tends to 0 relative to the metric d. However, the values of lambda at psi n do not tend to 0. Indeed, since lambda is linear, the absolute value of lambda at psi n equals 1 over n times the n norm of phi n times the absolute value of lambda at phi n. But the sequence phi n was initially chosen so that the absolute value of lambda at phi n exceeds n squared times the n norm of phi n. The resulting ratio equals n, so certainly the sequence of complex numbers lambda of psi n does not tend to 0. This contradicts the continuity of the tempered distribution lambda and concludes the proof of theorem 4.8. Let us repeat what we already said earlier, because it is so important. By theorem 4.8, the values of a tempered distribution are controlled by the derivatives of the input function phi up to some finite order. This is not so obvious from the definition. We then move to our first example of tempered distributions, example 4.9. Let p be an exponent between 1 and infinity, and let f be an LP function. Then f can be used to define a linear functional lambda subscript f, which turns out to be a tempered distribution. Namely, lambda f of phi equals the integral of f times phi for all Schwarz functions phi. This formula clearly defines a linear map on the space of Schwarz functions, at least assuming that the integral of f times phi always makes sense. This will follow from the next argument, where we check that lambda f is a tempered distribution. Let phi j be a sequence of Schwarz functions which tend to 0 in the metric d. Then we first estimate the absolute value of lambda f at phi j by pulling the absolute values inside the integral. Next, we use Hölder's inequality with exponents p and q, where p is the exponent relative to which f was assumed to be an LP function, and q is the dual exponent of p. We aim to show that lambda f of phi j tends to 0, and here the LP norm of f is finite. So what remains to be done is to show that the LQ norms of the functions phi j tend to 0. To estimate the LQ norm of phi j, we write out the definition, and then we decompose the absolute value of phi j to the power q as the product of the absolute value of phi j times the absolute value of phi j to the power q minus 1. In this expression, we simply estimate the second factor by its L infinity norm. What remains is the L1 norm of phi j. And of course, both of these factors need to be raised to the power 1 over q, but this makes no difference for the argument. Our assumption was that the functions phi j tend to 0 in the metric d, so in particular the L-infinity norms of the functions phi j, which equal the 0 norms of the functions phi j, tend to 0 as j tends to infinity. The same is also true for the L1 norms. To see this, one writes out the definition of the L1 norm and then divides and multiplies the absolute value of phi j x by the factor 1 plus the norm of x to the power d plus 1. Here, the product of the numbers 1 plus the norm of x to the power d plus 1 and the absolute value of phi j at x is uniformly bounded by the d plus 1 norm of phi j. So we may pull this norm out of the integral. What remains is the integral over Rd of the function 1 plus the norm of x to the power minus d minus 1. And this is just a finite constant depending on d. Now we have shown that both the L-infinity and the L1 norms of the functions phi j tend to 0 as j tends to infinity. It follows from this and our previous estimate for the absolute value of lambda f at phi j that the numbers lambda f at phi j tend to 0 as j tends to infinity. This means that lambda f is a continuous linear map on the space of Schwarz functions and hence, by definition, a tempered distribution. The previous example shows that the notion of tempered distributions generalizes LP functions. The next example will show that there are also plenty of other functions which are not in any LP space, but are nevertheless tempered distributions. Indeed, assume that f is a Lebesgue measurable complex-valued function on Rd which is polynomially bounded. There exists a positive constant c and a natural number n, such that the absolute value of f at x is bounded by c times the norm of 1 plus x to the power n. Then, as in the case of LP functions, we may associate to f a linear map on the space of Schwarz functions by the formula lambda f at phi equals the integral of f times phi. As an exercise, you can check that this integral is absolutely convergent for all Schwarz functions phi, and lambda f is a tempered distribution. It is easy to imagine many examples of functions which are polynomially bounded, but do not lie in any LP space. For example, any non-zero polynomial is such a function. Part B of example 4.10 generalizes the idea of polynomially bounded functions even further. Let mu be a Borel measure, which is polynomially bounded. In other words, there exist constants c and n as before, such that the mu measure of any ball of radius r centered at the origin is bounded by c times 1 plus r to the power n. Then the measure mu can be used to define a tempered distribution lambda mu by the formula lambda mu of phi equals the integral of phi d mu. This example generalizes the previous one because any polynomially bounded function f can be used to define a polynomially bounded measure, at least if we allow for complex measures. A noteworthy special case here is that every finite measure is polynomially bounded, and trivially so. Simply choose the constant c to be the total mass of the measure. Consequently, any finite measure mu gives rise to a tempered distribution lambda of mu. At this point, it might seem like everything is a tempered distribution. So let's have one example of a familiar function which does not define a tempered distribution. This function is the exponential function e to the power x. This function does not define a tempered distribution for the simple reason that e to the power minus x is a Schwarz function. And the integral of e to the power x times e to the power minus x is the integral of 1, which is infinity. The lesson here is that tempered distributions are, in some vague sense, polynomially bounded, and something which grows faster than any polynomial will typically not define a tempered distribution. In particular, locally integrable functions do not always define tempered distributions. Now that we have the definition of tempered distributions in place, we will next investigate some basic properties of tempered distributions. Of course, one of these will be the Fourier transform. This will be the content of the next lecture. This concludes lecture number 17 on the course Introduction to Fourier Analysis.